So I'd like to introduce Dan Honey, as I mentioned, our resident educator. He has a ton of experience in our industry, almost 40 years. He has his degree in chemical engineering. He has a degree in arts from London. He has been at a few different companies locally. He has been with us, Veritech, since 2016, and he was brought on to progress the high performance HVAC solutions in our region. So with that, Dan, oh wait, no, I think I have a couple more slides.
Yeah, I'm having again
Oh,
an advancing slide issue.
hmm.
Okay.
All right. So I just wanted to bring your attention to some of the publications that Dan has been involved with, co-authoring, either authoring himself or co-authoring with others in our industry in the local area, in the ES magazine. One of the recent ones, December's edition in 2022, was 100% outside air systems, passive radiant cooling and heating systems that he co-authored with Darren Alexander with TWA. And he has a 2023 edition in August for another article, Innovative Active Chilled Beam Design Approach for Building Humidity Control. That one was a mouthful. So with that, I will hand it over to you, Dan.
Thank you very much, Kelly, and thank all of you for joining us today for session number 7. It's hard to believe the year is almost done, but there you go, time flies. Today we're discussing a very important topic, in my opinion, but it's a topic that is gaining more and more momentum and gaining the attention of our industry: thermally stratified environments. So what are thermally stratified environments? But before we evaluate thermally stratified environments or whatever, first of all, we need to do is build a context as to why this HVAC solution is gaining the attention in our industry that it is. We're going to do some backtracking. We're going to review some earlier documents regarding COVID-19, certainly as we're moving into a new flu and cold season, and as there's growing momentum in our industry to ask how indoor air quality does impact human health and how can indoor air quality be improved, if not optimized, to reduce sickness within spaces, both short-term and long-term. If any of you watched 60 Minutes and you saw, I believe it was last Sunday or maybe it was the week before, 60 Minutes had a spot on the importance of indoor air quality and the built environment and its impact on human health. So indoor air quality is getting mainstream attention, and I think with what is being discovered and revealed, it's going to gain more and more traction. So we're going to look at, first of all, a review of how infection is spread in the space, and then we're going to move into the physics of room airflow and review mixed air systems. How does a mixed air system work? And what is its objective before moving into thermally stratified environments? Then we're going to look at displacement ventilation, the HVAC design strategy for creating thermally stratified environments. We're going to look at displacement ventilation for cooling, and then we're going to look at it for heating. By the way, our manufacturer for passive radiant cooling and heating panels and sales, TWA Panels, is located in Canada. So it is a technology that can be used successfully in very cold climates as well. Then we're going to look at the different types of displacement diffusers that are offered, and then how air handlers are configured in order to provide 65-degree air in lieu of 55-degree air, and yet have that air appropriately dehumidified. Then we're going to look at an innovative solution approach that creates the thermally stratified environment by creating a single pass of clean outside air across the breathing zone with no return air in the space. So let's get moving today. So today's discussion, We're going to review an article written in 2021 of the ASHRAE Journal. Actually, it was a two-part article series on minimizing transmission in high occupant density settings, because I want to reveal an important qualification in the article and how it makes the studies relevant or perhaps somewhat of a concern during our flu and cold season. We're then going to look at the physics of airflow in the conventional mixed air environment, and then thermally stratified environments, and then argue, hopefully, why the industry is looking at displacement ventilation in a post-pandemic era. So let's look, first of all, at the ASHRAE Journal May and June two-part 2001 article series on minimizing the risk of transmission. First of all, I want to introduce you, if I haven't already in previous presentations, to the Wells-Riley equation. It was actually written by two doctors, Wells and Riley, in 1978 to model the risk of infection during a measles outbreak in 1978. And its goal was to provide a simple and quick assessment of the infection risk. And it came up with a term called quanta. Quanta is a minimum infectious viral load, the minimum you need in order to come down with a virus or a bacterial infection. Then they introduced the term quantum, which is a dose of airborne droplet nuclei that results in 63% of susceptible persons being infected. Those are two terms used in these evaluations regularly, so if you come across them, here are your definitions. So the ASHRAE Journal article, part 1, introduced a modified Wells-Riley equation applied to a CFD modeling program. And the article evaluates and reviews a summary of field experiments used to determine whether the assumptions in the inherent Wells-Riley model in an indoor space is appropriate. But notice the qualifying term, well mixed. And this is a very important consideration. The article goes on to evaluate in the CFD model using a sodium chloride molecule as the agent to measure particulate dispersion throughout the space. And they did two particle sizes to see how gravity of a larger particle might influence the diffusion pattern generated from an infected occupant. The two particle sizes were 0.728 microns, and the other was 2.78 microns. And then they used the Wells-Riley modified equation to demonstrate that a particle of 0.728 microns does disperse more readily throughout the environment than the larger 2.78, because the larger particle will respond to gravity and drop out of the air more quickly than the smaller particle. Be aware when you're dealing with flu or COVID-19 pathogens, you're looking at particle sizes of 0.125 microns, 0.15 microns, so considerably smaller than that particle size used in the ASHRAE Journal article. In part 2 in June, there were some interesting findings that I want to make all of you aware of if you're in a position where you need to make this recommendation to an owner or a client on what solutions are demonstrated in the industry to be effective to reduce the risk of infection. Due to the CFD modeling, the following was determined: that looking at a mask effective filtration efficiency when occupants in the simulated space were given masks of various filtration effectivenesses, that a mask of 0.5 or 50% effectiveness, the conditional infection probability is reduced by a factor of 4. So that's pretty compelling evidence. And then if you use a more efficient face mask with 90% effectiveness, then the conditional infection probability is increased by a factor of 100. So that is yet another study that demonstrates the effectiveness of masks if we enter into another era of pandemic, or if you have a loved one who is susceptible to deficiencies or immune compromised condition, then wearing masks makes all the sense in the world, at least according to this article. It also went on to demonstrate air change rates in a space impact the risk of infection. By increasing the air change rates to a space from 1.34 to 3, you can actually reduce the risk of infection by 2 times. The article in part 2 goes on to demonstrate that if you use a combination of a mask and increasing the air change rates in a space to 3, you can reduce the risk of infection by 8 times. So anyway, the problem is that this article was created or was meant to simulate a condition in a well-mixed environment. And that begs the question, when is a mixed air system properly creating a mixed environment? Well, it's during peak load conditions when air supply diffusers are injecting air into a condition zone at maximum velocity. At maximum velocity. The design challenge, however, is that what if you're not at peak summer design condition? What if you're at part load and you're in a VAV system and your VAV box throttles back, restricting air at diffusers? Does your room maintain a mixed air environment? Well, when is the VAV system at minimum load? It's during our driest times of the year. Fall, winter, and early spring, otherwise known as cold and flu season. So a mixed air environment during a period of time when we are most contagious or most susceptible to infection occurs when we're at part load conditions, and those conditions don't comply to the ASHRAE article that I just referenced. So be aware of that. And that's an important point as we begin to evaluate what a mixed air system is. Just to touch base on it, many of you already know, but let's just go back to basics for a minute. The purpose of a mixed air system is to really address human comfort, and then also to address dehumidification, maintaining proper humidity levels within a space. But thermal comfort is the primary purpose. And to do that, according to Dan Inhout and ASHRAE Standard 55, a temperature differential of plus or minus 2 degrees has to be maintained throughout the cubic volume of space. So rules for a fully mixed air system, as Dan Inhout expresses, is to create a space temperature in well-mixed spaces that are uniform and within the 2-degree tolerance that I had mentioned. Temperatures should also remain the same throughout the day, and the room must be relatively free from objectionable air currents to maintain a proper thermal comfort. To achieve a mixed air environment, 55-degree air is injected at the space at high velocity, at 150 feet per minute. Diffusers don't like to see air faster than that, or even sidewall registers, because you can start getting into sound issues. Diffusers can start humming, if not whistling. So 150 feet per minute is usually peak discharge velocity, and 55 degrees because that is the temperature of saturation. When air is at 55 degrees, it condenses water vapor into liquid, which is a condition seen at the cooling coil of air handlers serving these systems. So air is supplied into a room at a high velocity. In order to have proper mixing, air must achieve what is called Coanda. You wouldn't want to provide a diffuser hanging open in an open space without some type of beveled edge designed for the application, because air will not inject far into the space, and achieving a mixed air environment will be difficult at best. So having the supply air jet travel along a surface results in what is called Coanda effect. Coanda effect is the effect of a moving jet of air that attaches to a parallel surface because a negative pressure zone generates between the airstream and the surface that allows the airstream to hug that surface. And with that reduction of pressure, air can throw further than a diffuser free suspended in open space. And so that is why high discharge velocity along a surface for conventional diffusers are used. So establishing Coanda requires high velocity discharge. Now, as that air is discharged into a space, it induces room air into the supply air jet. The supply air jet slowly begins to warm and reduce in speed because of the greater mass. And consequently, air begins to travel down into the space where, per ASHRAE Standard 55, you want to have a terminal velocity at the occupied zone of approximately 50 feet per minute. But to do that, you have to have air achieving Coanda at the diffuser or at the surface of the ceiling diffuser to provide the appropriate induction of room air into the supply air jet to create a mixed air condition. So looking at some CFD models, in order to create uniform mixing, we have to have proper velocity discharge at the diffusers. If you look, however, in a VAV system, when we're at part load, then all of a sudden the air to the diffusers is restricted by a variable air volume box that a damper approaches a closed position because the room air thermostat is satisfied, and as that thermostat controls the damper to a closed position, air is restricted, discharge velocity out of the diffusers is reduced, and consequently negative buoyancy takes over and air begins to drop into a space. So this is a condition in a lot of institutional buildings with VAV systems, even office buildings, a lot of larger office buildings especially, that you do not have the proper discharge out of a diffuser or discharge velocity to maintain a properly mixed environment that will allow for a more effective dispersion of contaminants released into a space. There is a solution for that, and healthcare has discovered what that is, and that is to use your VAV box as a constant volume box 24/7, or certainly during occupied hours. Let the air be at a fixed velocity, and then use reheat by increasing the supply air temperature when the thermostat is satisfied from 55 degrees to 70 degrees, 75, 80 degrees, using SCR technology in order to raise the supply air temperature while maintaining velocity. However, reheat is very expensive, it is very inefficient, and not the solution, certainly per ASHRAE, as they are moving in the direction of decarbonization and sustainability. So keep that in mind. So what are thermally stratified environments? We've all experienced them. Certainly if we've been in a swimming pool, and certainly in a mountain, swimming in a mountain lake. A thermal stratification is a temperature differential throughout a continuous body. And if you've been in a mountain lake, you notice that the water at the upper levels of the lake are warmer than down deep. And that's because radiation cannot penetrate far enough through the liquid in order to radiate or heat the lower levels of water. So it's much cooler. So you have a variation of temperature throughout the body of water. Well, can you do the same with air? And the answer is you can, because air, like water, is a fluid. But unlike water, it is not a very dense fluid. So in a thermally stratified environment, you normally see a room set point temperature of about 75 degrees, 73, 77, depending on set points, etc. But you supply 65-degree air to the space, and you provide it at low velocity, so air pours into the space that allows cool air to fall to the floor, warmer air to begin to rise, and to create the profile you see in the graphic on this slide. Temperature differentials in a conventional space with 9 to 10 foot high ceilings is roughly 70 degrees at the floor, 75 degrees at the thermostat, and in the upper levels of the room, 78 to 82 degrees, depending on how much heat is generated in the room and the amount of air supplied to the space. So unlike a mixed air system that requires fan energy to drive the air at high velocity in a space to create mixing, what is elegant about a thermally stratified environment is it's the force of nature that conditions the space. It's called the force of convection. Wherever there's a heat force in this, or a heat source in the space higher than the room air set point, the warm air from that source will rise to the upper levels of the room, where any air contaminants entrained in that rising thermal plume is lifted out of the occupied zone into the upper levels of a room. So this is one of the elegant features of displacement ventilation, is that fan energy is not required to drive the air, providing you maintain the temperature profiles, 75 degrees on the thermostat, and hopefully an occupant has a body temperature of 98 degrees. Roughly, on average, about a plume at a velocity of 30 feet per minute rises off that occupant to the upper levels of the space. So how does it actually work? Well, we have a video here from our manufacturer of displacement products, Kruger, that'll give you a visualization of what I'm actually discussing. If you can see my cursor moving, I'll try to explain what is going on as soon as the video loads here. You will notice that on the opposite side of the room, there are two white columns, and those are the displacement diffusers. And in this smoke test, the cool air supplied for this diffuser will emanate smoke at low velocity, roughly no more than about 40 feet per minute, and we'll cover that a little more closely. And as you see the smoke pouring out of the diffusers, on the opposite side of the room, there's a heat source. And that heat source has a convective thermal plume because warm air rises, cold air falls. And you'll see the smoke from the supplied air becoming entrained in that convective thermal plume and drawn up to the upper levels of the room. And ASHRAE documents state very clearly that contaminants have a tendency, in fact, they do follow the flow of air. So at 30 feet per minute plus, or whatever the temperature of the object emitting the plume, that room contaminated air will be lifted up into the upper levels of the room where your return and exhaust grills are located. So as you can see, what moves air in the space is convection. So an occupant who is looking to be comfortable, they're their own HVAC system, you could say, because wherever they walk in the space, they will have their thermal plume and they will continue to condition themselves with room air. Consequently, this vertically rising air creates a cleaner breathing zone for occupants. And the graphic of the beakers gives you a pretty good visualization of what I'm talking about. And so it begs the question, using and adopting this air stratification strategy, does it create a healthier environment? Well, ASHRAE says so, and we'll explore that a little more closely. But here, notice the difference of the supply air velocity off the diffusers into the space. Unlike 150 feet per minute, air is supplied at peak velocity of 40 feet per minute. You want the air to pour into the space. In places that have higher loads, a lot of foot traffic, you don't have sedentary occupants, you can bump that discharge velocity to 50 feet per minute. I've heard up to 60 feet per minute for airports, etc. But for offices and classrooms, 40 feet per minute is a good ideal target. These systems can be variable air volume, and you can get penetration of air down to as low as 20 feet per minute. So it's pretty interesting that with a thermally stratified environment, a continual flow of air is always moving upwards throughout the space at wherever there is a heat source. So what is the HVAC solution to create a thermally stratified environment? It's known as displacement ventilation. And I've been promoting the technology for, over 13, 14 years, and have had wonderful success with the applications that I've had. Occupants do not complain of drafts because we don't have air at high velocity targeting certain regions within a space, because any heat source generates their own plume and their own source of clean conditioned air. So looking at displacement ventilation, be aware that displacement ventilation does not condition the full cubic volume of space. You don't run a load count for the full cubic volume of space, only for the occupied zone. And that is defined by ASHRAE Standard 55 as 6 feet off the wall, off the floor, and 1 foot in from the walls. So the upper level sensible load heat gain due to conduction from a hot outdoor ambient condition, lighting in the upper levels of the room or whatever, will not be factored into the load calcs in the occupied zone. However, they will be calculated in the sizing of the cooling coil that will see the return air and mixed air condition at that coil. So 65-degree air is provided in lieu of 55-degree air. And this is very, very important, especially in Arizona's dry climate during our shoulder seasons, because at 65 degrees, our conventional economizer hours in a mixed air system from roughly about 17% annualized hours can be bumped, can be doubled up to roughly 34 to 35% of annualized hours. Well, this free cooling does have a significant impact on energy performance. By the way, we're working with Smith Group on the Banner Health Maricopa Clinic, the first Banner clinic to use displacement ventilation out of 7, used instead of 1 to 1.1 CFM per square foot, frequently used to design facilities in Maricopa County and our Sonoran Desert. They designed a 0.0 CFM per square foot. And it wouldn't surprise me with our LED lighting and our tighter buildings, we may be even to go lower than that, but it would have to be evaluated on a building by building case scenario. So how does displacement ventilation work? I've already mentioned that the discharge velocity out of diffusers are at low velocity of roughly 40 feet per minute. Air is supplied at between 62 to 68 degrees, and the upper level of the room is labeled drifts up to 80 to 85 degrees, where the high level return and exhaust grills are located. People can ask, well, won't people notice their feet are cold and their head warm? No, providing the temperature differential from the floor to the 6 foot height of the occupant doesn't exceed 5 degrees for a standing occupant, or if you're using this excellent solution for an auditorium, then it would be 3.5 degrees for a seated occupant, temperature differential from the foot to the head. So if you stay in this range, then you won't have thermal comfort complaints. And that was actually evaluated by the VP of Engineering at Price Industries, Jerry Sipes, personal mentor of mine, who actually did that study when he was getting his PhD at the University of Kansas. And I've certainly not been challenged with cold feet in a displacement design. Does it create a better indoor air quality, this vertically rising mass of air throughout the cubic volume of space? Well, ASHRAE thinks so. ASHRAE 62.1 allows for an engineer to design with 20% less outside air if low in-wall or underfloor displacement ventilation is used, because it generates cleaner air at the breathing zone for reasons already discussed. So ASHRAE refers to it as a 1.2 zone air distribution effectiveness, and I invite you to look at the standard to see how you can take advantage of that. And if you can reduce the outside air, you're going to certainly reduce the building load of your system. So what does this mean with regard to the pandemic that we discussed earlier? Well, I invite you to look for a Nature Journal article called The Quantitative Evaluation of Precautions Against the COVID-19 Indoor Transmission Through Human Coughing. It's a CFD evaluation that arrived at the following conclusions using a Eulerian Lagrangian CFD particle tracking model commonly used in pathogenic evaluations through CFD. The result shows that implementing upward ventilation is the most effective measure, followed by wearing face masks. Again, that supports the ASHRAE article I alluded to earlier. It goes on to say that the soundest solutions for reducing the risk of infection is the combination of the face mask and upward ventilation, which, according to the model, showed that there can be a 99.95% reduction of infectious concentrations at the breathing zone. So that's a pretty powerful statement. Obviously, we want to look at validated tests, studies, white papers to earn our confidence that it's the right solution, but I've yet to be challenged with any new information that would suggest otherwise. So again, a reason to support using displacement ventilation in thermally stratified environments for creating healthier buildings. So this is very good, but what about displacement ventilation in heating mode? We've been talking about displacement ventilation in cooling. Can you heat with a displacement ventilation system? And the answer is you have to be very careful. Well, not very careful, you just have to follow the rules of physics. The challenge is that if you provide warm air off of a diffuser at low velocity, thermal buoyancy takes over close to the diffuser, and that warm air discharged at low velocity all of a sudden succumbs to convection once released into the space. And that warm air will not mix in the space, but will rise to the upper levels of the room where it will have little to no impact on the thermostat. So you have to be strategic. Displacement diffusers work well at low velocity discharge at 2 to 10 degrees below space set point, up to 0 to 5 degrees at conditioning bringing load neutral air. But if the supply air temperature exceeds 5 degrees of temperature set point, you will have thermal buoyancy taking over and your warm air discharged to the upper level of the room. So how do you heat appropriately, especially in perimeter zones, with a displacement ventilation system? The heating system is usually considered in parallel to the cooling displacement application. For colder regions, there could be perimeter radiation applied. There can be ceiling radiant panels or convective sails that as we've seen installed at ASU's new ISTB7 project. There's also a newer product, it's probably about 6 or 7 years old, that is a combination heating and cooling ceiling displacement ventilation system. I've had very good results using ceiling displacement ventilation for the Banner Health Clinics and for the Banner Boswell 26 patient room renovation project here in Phoenix, Arizona. And what it is, it's a 2-tiered plenum sheet metal box that sits on the top of a diffuser with a large area perforated plate for displacement ventilation in cooling mode. And then in heating mode, there's a 2-position damper that modulates to close the air serving the cool air diffuser plate and injects the warm air into the linear diffuser where there's very little face area. So you achieve high discharge velocity, and allowing this device to wash perimeter walls and windows in heating mode. This is the solution that was used at the Banner Boswell patient space renovation project, and we never had a thermal comfort complaint using this solution. Using ceiling displacement ventilation, however, you will not gain the advantage of the 1.2 ventilation effectiveness mode offered by standard 62.1. So be aware of that. But it does offer you a lower first cost because you can run flex duct to these devices that is a cost savings versus running sheet metal duct down in walls to low in wall diffusers. You can also use baseboard radiation, hydronic and electric solutions. And then you can use radiant panels and sails around perimeters of buildings in order to heat during our somewhat temperate winter season. This technology has worked very well. I've had more luck with hydronic radiant panels than electric panels because there's a time for the electric panel to warm up adequately for the brief moments of occupancy where we've used it in medical office buildings and exam rooms. And so the electrical output of an electric radiant panel needs to be taken into consideration. However, with hydronic panels, they're fast reacting and we have not been challenged with that design. So what are the displacement ventilation products that create thermally stratified environments? Well, they look considerably different than our conventional registers and diffusers, that's for sure. However, I've known architects to be rather attracted by the way they look because they can be integrated somewhat easily into more visionary, creative architectural designs and within the space, and allowing ceilings to be free of ductwork. There are rectangular box designs, circular designs, semicircular, corner, and also recessed in-wall designs. And all of them work just the same. One way to understand how much square feet of diffuser face area is required to a space is to recognize you calculate the amount of air necessary to meet the space load in the occupied zone, and then you take that amount of air and you divide it by 40, and that'll give you the square footage of diffuser face area to evaluate architecturally and how that might be installed within the space. Again, there are lay-in ceiling diffuser applications. This diffuser shows a cooling only, which we can do, which is what we applied for the Banner health clinics throughout Maricopa County and in, as I understand it, in Colorado as well. However, again, you will not find that this solution, though a lower first cost with regard to ductwork, will not offer an owner the 1.2 zone air distribution effectiveness, and consequently will require the added outside air depending on the municipal authority in charge. There are also 180-degree diffusers, 360-degree diffusers that are used to create full columns in large open areas. And it begs the question, if you do have a large open dining area with 15 feet ceilings, is it really necessary for thermal comfort to provide 75-degree air at 12 feet above the floor? That's a lot of energy to maintain that uniformity of temperature in spaces with large ceilings. Another excellent solution, and a solution that I think really hasn't gotten its due recognition, and I sort of understand why, and there's a good reason why I won't go into right now because we'll cover it in the underfloor presentation in December. And those are underfloor air systems. Underfloor air systems do create thermally stratified environments. There is a proper, fully thermally stratified environment offered when an underfloor system uses a displacement style floor diffuser. These diffusers will probably inject roughly about 50 CFM per diffuser, maybe 45. So you need a number of diffusers to provide the amount of air necessary to condition the space. The earlier form of underfloor air system used what is called a semi-turbulent design that injects air at higher velocity, roughly 70 to 80 CFM per diffuser at a floor plenum pressure of 0.05 to 0.08. And that air supply terminates at roughly 5 to 6 feet to create a micro mixing zone within the occupied zone. Thermal stratification does occur, and ASHRAE 62.1 now recognizes, though it didn't originally, that a semi-turbulent design is conducive to a 1.2 ventilation effectiveness. And so something to be looked at. The advantage of this system is, though you have to be careful where these diffusers are located in relation to sedentary occupants, there are fewer diffusers. So the UFAD system becomes less expensive, and that may be a consideration depending on available budgets. So having spoken to displacement ventilation, the providing of 65-degree adequately dehumidified air begs another question. How do you lay out the air handlers? What does the air handler look at? Well, it isn't like your conventional design with a fan, cooling coil, and a filter bank. It's a little different. Why? Because you have to be very careful on making sure you have adequate dehumidification at the cooling coil in order to maintain your space humidity levels. Just supplying air condition to 65 will not provide adequate dehumidification, if any, and consequently, a humidity problem will certainly occur in most buildings. So how do we do that? How do you create a supply air jet that is adequately humidified, but yet is supplied to a building at 65 degrees? I've had very good luck in our market using a strategy called side stream bypass. With a custom air handler, you actually provide a secondary tunnel adjacent to the cooling coil, and you have a modulating damper that regulates the amount of mixed air that is bypasses the cooling coil and reintroduced into the supply air stream to create a free reheat mode from 55 to 65 degrees. A discharge air temperature sensor is placed at the air handler that modulates the mixed air damper, and that damper modulates open and close to maintain the supply air at 55 degrees. The question is that you need to make sure that the cooling coil has a low enough dew point temperature to absorb any moisture in the mixed air stream to maintain a discharge humidity of roughly about, I would say, 50 to 48 degrees minimum to properly dehumidify a building. So also in this system, you can take advantage of our economizer hours, and that should be built into the side stream bypass to go into economizer mode, where no supplemental cooling might be required during our moderate, dry, temperate months of the year. So using side stream bypass and face and bypass dampers is one solution that I've had good success with that in our industry. Here's an example of the air handler we laid out for a customer at the Banner Boswell campus, where a side plenum was added to circumvent the cooling coil. Here's your modulating damper. Your discharge air temperature sensor would be placed on the discharge of the unit, and this damper modulates open and close to maintain 65 degrees when your dehumidified air is provided off the cooling coil. Another solution that we use in a project in ASU is a dual wheel solution. An enthalpy wheel to precondition the outside air to add a layer of efficiency, and enthalpy wheels are significant, as my previous psychrometrics presentation illustrated. However, a second sensible heat transfer wheel is added, where we use 75-degree room air or building air to post-condition the air off the cooling coil to 65 degrees without adding reheat. The problem with this solution is that you are adding static pressure, so there'll be more fan energy required to provide the air necessary to condition the building. But it is very good, and it eliminates the humidity issue of a mixed air side stream bypass solution. Another solution that should be given every consideration are the latest in 100% outside air and also mixed air DX units now. I think Daikin manufactures units up to 75 tons, and these units are excellent for providing proper dehumidification off the cooling coil and using hot gas reheat on the discharge of the unit in order to elevate air off the cooling coil up to the necessary 63, 65 degrees without using supplemental energy. It uses the heat of rejection off of the compressors and sends that warm refrigerant to the bypass or to the hot gas reheat coil, where we have free post healing off the cooling coil. And so this system is a very very good for a displacement ventilation design, especially for smaller mid-sized buildings, 30,000 to 50,000 square foot, using package DX solution. And if you add a enthalpy wheel in these units, which is a standard feature, you can also provide another layer of energy efficiency to your system. So very, very interesting solution. The Daikin Rebel uses variable speed compressor technology. They can come with energy recovery wheels, ECM fan motor technology, and they can also be applied in a variable refrigerant system. Have you ever thought of a variable refrigerant displacement ventilation system? Is it doable? And the answer is it is. Yes, it is. So just be aware of that. And then, of course, you can get larger custom DX units as well for those applications, custom designs. We've had good success with a manufacturer called Annex Air, and as well as Nortec Air Solutions also has some design configurations that might be considered. So let's take it to another level, and let's take the technologies that are available that are not new technologies. It's just how we reconnect the dots to heighten efficiency and to create clean environments for occupants so that we maximize the health of the occupants in a space. Let's look at a system that I think should be given every consideration, and it's an innovative application of 100% outside air, underfloor air systems. Talking to our underfloor manufacturer, Mike McQueenie, who will be available in December when we do an underfloor air symposium in Phoenix that we invite you to personally attend if you can do that. What if you used an underfloor air system with displacement ventilation that is 100% outside air, no return air back to the building, no active agent pathogens being entrained in the return air and resupplied to the building because of MERV 13 filtration? What if we just control the air change rates to a space using 100% outside air, and outside air only crosses the breathing zone in a thermally stratified environment? Is that doable? And the answer is yes. With our manufacturer's air fixture and our radiant manufacturer TWA panels, we can evaluate this system. And what that might mean for energy performance, I believe would be very, very attractive. And even more importantly, I think it would offer the most optimum indoor air quality to reduce the risk of infection and short and long-term illness due to VOCs, carbon monoxide, CO2, etc., that are often major components within the indoor environment. And then you can use an underfloor displacement 100% outside air system with other supplemental layers of protection, UV lighting, ionization, enhanced filtration technologies. We've picked up a new line of filters that offer MERV 14 effectiveness at less than 0.1 inch of pressure drop across the media, with filter change-out rates of 1 to 1.5 times or every 1 to 1.5 years. So this is certainly doable. And then if we added humidification to these systems, there are ways of controlling your indoor air quality efficiently, so an owner is not paying an operational premium to create the environment that his employees or occupants might seek to have. So quickly in review of today's presentation, we covered indoor air quality and the risk of infection as proposed by the ASHRAE article in 2021. We looked at mixed air systems and thermally stratified environments and why convection is conducive to a cleaner air condition at the breathing zone. We looked at displacement ventilation, the HVAC strategy to create thermally stratified environments, and how it might be applied both in cooling and in heating, and the type of devices utilized to create the necessary indoor air environment. And then thinking outside the box and reconnecting the dots in a new configuration, why would we not look at optimizing system performance and indoor air quality, looking at 100% outside air passive decoupled radiant systems. Any questions?
All right, so looking in the chat, I did see a question earlier, but I wasn't quite sure exactly what you were talking about, Kelly Lim. You asked who in healthcare discovered that. I don't know if you want to clarify that in there. The symposium that Dan was talking about, we are looking at tentatively December 14th-ish, either that week or the week before. We have not set it completely in stone yet. So we will send out an update once we have that date locked in.
Okay, very good. Now, the question, who in healthcare discovered that?
Yeah,
What
so there
is
wasn't anything else with it. So,
Um,
oh yeah, you want to ask it?
I think that was just before the slide on thermal stratification, like on reheat. I don't know which slide specifically, but you mentioned that it was discovered in healthcare. I was just wondering who had discovered it, so I can go talk to them.
Discovered displacement or reheat in healthcare, or?
Maybe if you could go back to the slide.
I'll be happy to.
Yeah, you were 23 minutes in when when she asked.
All right.
So probably towards the beginning.
Let's see what we can do to get this answered. 23 minutes in. Reheat, is this the slide you're referencing?
Yeah, I think that's when you had mentioned that it was like someone hit in healthcare had discovered.
In healthcare. Well, in healthcare, I use the application because per ASHRAE Standard 170, your air change rates are fixed per space, regardless of the load. So you have a constant flow of air in the space. And in order to condition the space temperature, out of a VAV box, you have a reheat coil that temperature of the reheat coil increases or decreases to maintain the temperature while the air changes in the space remain the same per ASHRAE standard requirements. I was at a chill beam conference and at the ASHRAE AHR Expo, I think it was in 2016, no, it would have been 2017. And Ken Laudermilk gave a presentation on the application of chill beams in healthcare. And he made the comment that reheat is one of the biggest energy penalties in healthcare facilities. So that is one reference. But who defines the air change rates in healthcare is ASHRAE Standard 170. And consequently, the only way to regulate temperature is to increase the supply air to the space in the event the space is overcooled. Did that answer your question?
I guess that wasn't quite my question, but you answered it. I think you gave me a better answer than what I was hoping for. So you can just disregard my question.
Okay. Well, no, see, everything, certainly with healthcare, do you work with healthcare?
Yes. I'm actually up in Canada, in Vancouver.
Okay.
Authorities.
Yes. Well, in the United States, ASHRAE Standard 170 is the standard that's used for healthcare design, and it assigns air change rates to patient rooms, which I think is at 6 air changes per hour, 12 air changes at airborne infectious rooms, protective environments are at 12 air changes, and operating rooms per the standard is 20 air changes. So the only way to condition the space is to have reheat to the VAV boxes that hold that air at constant flow rates in order to maintain a space temperature set point.
All right, we have another question that came in. What do you
Yes.
see as the barriers to a wider uptake of displacement ventilation?
What are the barriers to it? Perceived first costs. Perceived first costs. I could see where low in wall sheet metal ducted displacement ventilation will be at a cost premium to a building owner because of the added sheet metal. However, I don't believe that would necessarily be the case for overhead displacement ventilation or for underfloor ventilation. what I've found with advancing 100% outside air chill beams and passive radiant cooling and heating systems is that if these systems are being considered and being evaluated in early design, please make sure the full design team, the engineer, the architect, the contractor are involved in being aware of the architectural savings these systems offer. For example, underfloor air systems can now be designed to 8 and 10-inch plenum heights. You don't need 16-inch plenum heights for fan-powered terminals, and that we'll cover in the next session. What does that mean with regarding the opportunity to lower floor-to-floor heights in a building, and what does that mean financially to the building? And this is the type of dialogue that needs to occur. And I'm going to give you an example of a project here in Phoenix for the U of A Medical Center, the U of A Cancer Center here in Phoenix. It's a 6-story, I think it was 130,000 square foot, 140,000 square foot facility. And early on, Affiliated Engineers, AEI, wanted to look at 100% outside air chill beam system versus a medium pressure VAV system. And during the initial budgeting of a mechanical to mechanical comparison, the 100% outside air chill beam system came in roughly $300,000 to $400,000 over and above medium pressure VAV. So I asked the lead engineer for that project, who I believe was Charlie McGowan then, and I asked him after the project went in, what decided that system to move to chill beam? He said the architect was able to lower the floor-to-floor heights 1 foot per floor, and they saved $2 million architecturally to that building. So that's substantial, which begs the question, really, which system offered the owner the best value? Not only was it the most efficient system, so the owner continued to benefit from the reduced operational costs of the chill beam system, it was a lower building first cost solution. We saw that with variable refrigeration and evaluating electrical loads from 115DX, cheap, lowest first cost, versus 480 volt, 3-phase variable refrigerant. And we saw a significant reduction in the electrical load that begged the question that VRV was actually a cheaper first cost solution for the owner because the electrical component was taken into account. So in answer to the displacement ventilation, it's a case by case. What type of building is being designed? What type of airflows are being required? What is the vision for the project? And instead of shoehorning a mechanical system into place and hoping that it's cost effective, bring the team on board that understands the system so we can take full building advantage of applying these more innovative technologies.
So they'd also responded in the chat that they'd only seen DV applied as part of a 100% outside air approach. Have you seen it applied as part of a design that includes return air? Is this beneficial? This relates to cost, and that my understanding is that DV, in conjunction with its complementary strategies, including 100% outside air, can lower floor-to-floor height. So you kind of you touched on that.
Yes. Well, yes. In fact, all the Maricopa health clinics had a mixed air component at the coil. They were actually bringing return air back to the air handlers serving those designs. And the same was true with the Banner Boswell unit. It dealt with a mixed air condition. So in that application, there could be a challenge of actually reducing floor-to-floor heights unless they were 100% outside air solutions, because then you design at a lower CFM per square foot. In Phoenix, we see 0.3 to 0.35 CFM, maybe 0.4 per square foot of space versus 1 to 1.1 CFM. And it's the reduction of ductwork. And also with the new technology today with air handlers, we can shrink the equipment square footage requirements depending on the system applied.
So with respect to humidification in the cooling cycle, are you completely removing humidity in the supply airstream? Wouldn't some humidity be required for comfort? And then in the heating cycle, is the same occurring? Again, wouldn't we need some humidity for comfort?
Absolutely. It is well known in the industry, and it really reached a focus during the pandemic, how properly humidified environments between 40 to 60% RH are more effective at reducing the risk of infection than drier environments. And when is our driest time of the year? November, December, January. So absolutely, humidification in a displacement ventilation project is certainly doable, providing the owner is confident they can control the humidity in the space. So humidifier systems can be added to a system. Now for dehumidification, I invite making sure that the dew point off the supply air coil is not only low enough to absorb the moisture gain in the building from occupants, running water, maybe fountains, etc., and outdoor air humidity, but it also has to have a low enough dew point to take in the humidity component in the side stream bypass as well. And in my psychrometrics deconstructed 2 presentation, I illustrated that psychrometrically on what conditions. It could be, with the case that I showed, that you would need 48-degree dew point off the coil to at least approximate dew point at a room condition to 75 degrees, 50% RH. So maybe you need a dew point of 45 degrees off the cooling coil to absorb the moisture content in the mixed air stream, dumped back into the supply air jet before leaving the air handler.
So jumping back to the barriers, so the Alex who asked this question, he actually just had to jump off, but he said his understanding of some of the other barriers which you are helping to overcome with this presentation is a lack of understanding of engineers about how to design it, and in addition, the onus on the engineer of record to demonstrate the equivalence. So we're helping overcome that right now with our presentation.
Well, that's good to hear, because
yes.
Our manufacturer, Kruger, for displacement diffusers, they'll actually do throw patterns of air at 40 feet per minute discharge, 20 feet per minute discharge over an architectural space. If we can have drawings, CAD drawings of the space, we'll do a throw evaluation through our manufacturer. And for an engineer to look at and to evaluate, makes all the sense in the world that we have any representative who is trying to advance displacement ventilation would participate with the engineer in evaluating proper layout. Here's displacement ventilation, Mr. Engineer, figure it out. We're here to support these technologies. And that's part of really the Veritech Technical Institute is for underfloor air systems, air fixture, they'll lay it out. The engineer can modify it, they can adjust it or whatever. Of course, we would expect that. But we can participate in these evaluations, and even in radiant cooling and heating, we would run the first pass of layouts for evaluation. So we would not expect to throw this design concept into an engineer who has not had much experience and wish them
good luck.
best of luck.
Well,
Right.
it sounds like we're on the right path with our education, then. So good to hear. That is it for the questions, except we are being asked if we want to come work in Canada. Only in July, August, and September.
Well, my wife and I are hoping to be in Vancouver in June. So
well, there you go.
Okay, please give me your contact. By the way, Alex Hutton is my colleague.
Oh, okay, perfect. Okay.
Health authorities, and she.
Okay, sorry.
To advance displacement ventilation within the health authorities and at hospitals and long-term care.
Perfect. Okay.
Thank you.
Interesting. Kelly, thank you so much for joining us.
All right.
Thank
so
you
that
so much for having this presentation. This is amazing.
Awesome.
I think you've been so far the best presenter on this topic.
Well, thank you very much. I've been doing it a while.
Okay, so with that, sorry, the tickle in my throat is back. With that, there are no more questions in the chat, but as always, anybody left on the call, if you do have more questions, you can feel free to reach out to Dan or myself directly, always to your salesperson through Veritech, and we are always more than willing to do as many presentations as you want to get it all. So thank you, Dan. As always, a wonderful presentation.
Thank you, Kelly, and thank all of you for joining us today.
All right. Thank you, everybody. We'll see you next month.